So before we dive into evolving data pipelines and scale, a few words about me and my background. So I'm a co-founder and a chief architect at Tobiko Data. I lead the development of SQLMesh, the open source data transformation and modeling tool. Raise your hand if you heard about SQLMesh before. Okay, that's a decent number. Very cool. I have over 10 years of experience building various data and ML infrastructure solutions. Most recently, I did that and some of the data engineering work as well at companies like Netflix and Apple. Now you know who I am, but why am I here? I'm here because I believe that we, as data practitioners, face a series of challenges that have long been addressed by our fellow software developers. For example, creating development environments for data. How do we even create development environments for data? Do we ask the infra team to provision a schema or DB instance for us? How many environments do we need? Is it one per user? Is it shared between multiple users? How do we ensure isolation when we test multiple changes concurrently? Do we need to go through this process all over again every time we make a change? All right, assuming we figured the creation part out, how do we populate those environments with relevant data? Should we just sample production data or maybe generate some synthetic data? Is it really representative of data that we're going to face in prod? Of course, we can copy the entire production in development, right? That's probably better, but certainly not very runtime efficient. Because of these challenges, our development iterations are slow. We have to wait a really long time for the environment to provision, for the computation in dev to finish in order to preview and test our changes. Alternatively, we resort to testing only a subset of our changes, leading to catastrophic consequences in production. Or we decide to use incomplete or inaccurate data for our testing with a more or less same outcome at the end. Finally, production deployments are ad hoc and error-prone. There is just no established process for that. So for example, when I worked at Netflix, and Netflix has a very strong data team, both infra and engineering side of it, we would run outer table statements manually against production tables in order to apply our changes. I mean, back then, Netflix hired only senior engineers, so it probably worked for them, but this is definitely not a scalable process. It's also super stressful, by the way, because you have to double and triple check every time you apply a change. So how do we move away from this kind of flow? How do we make sure that the changes that we apply don't leave production in an incomplete, partial, or broken state? How do we quickly revert our changes if such a situation did occur, despite our best efforts, of course? Long story short, all of these factors make us a lot less productive than we could have been. Now, on the topic of scale, all of the challenges that I described so far, although they are universal, they become especially pronounced at scale. And when I say scale, many of you are probably thinking something like this. But the size of your data is only one measure of scale. Another measure of scale that is a lot relevant to what I'll be talking about today is the organizational scale, or organizational complexity. Remember the last time you tried to explain the lineage of your data to a teammate or stakeholder? The complexity is real. And it can be measured by, for example, a number of people who are involved in building, maintaining, and using analytical pipelines and data set in your company on a daily basis. Or maybe just a sheer number of analytical pipelines and data sets in your organization. So I'm done with memes, by the way. So I'm here to offer you 3 pillars of data productivity. The first pillar, data versioning. To maintain a historical record of changes and to be able to switch between different states of data freely. Second pillar, virtual data environments. To create isolated development environments populated with representative data in a fast and cost-efficient manner. Automatic data contracts. You probably hear about data contracts a lot these days, huh? But what I mean here is ability to assess the impact of a change and identify breaking changes. And what makes them automatic is the fact that you don't need to write a bunch of YAML. Finally, these three pillars support fast, safe, and cost-efficient development process, the nirvana state that we all strive for. So now we are going to build this little Parthenon together, brick by brick. And it's going to be a very dense talk. And I know that you guys are tired, but please do bear with me and make sure not to blink. And then come find me after the talk for a more in-depth conversation. When talking about data versioning, I don't mean versioning of like physical objects or tables in data warehouse or data lakehouse. This is a more or less solved problem. What I mean is versioning of something more high level than that. Something that I'm going to call a model. And I'm going to refer to model a lot throughout this talk, so I need to explain this concept first. So if you are coming from the DBT background, you already know what a model is. But if you're not, when I say model, I mean a transformation process, basically T and ETL. And one way to express transformation is using a SQL query. So here we have something very simple, right? We project columns A and B from some source, and we filter rows in those columns by column C, which should be greater than 0. Now, the SQL query itself is not enough for model to be a model. There should also be some sort of execution process which evaluates the query and stores the output that is produced in some data object in a data warehouse, like a table, a view, a materialized view. Let's summarize. So in order for the model to be a model, there should be a transformation logic defined, for example, in the form of a SQL query, some sort of an execution process that evaluates the query, and the data object where results are stored and become available. And when I say data versioning, I actually mean versioning both sides of the arrow, not just one of them. Now, model attributes. Model may have various attributes. And I'm going to divide those attributes into two groups. The ones that impact the data, impact the outcome, and the ones that do not, that they are basically metadata. So the attributes that do impact data include model query, for obvious reasons. This is basically our transformation logic. The type of data object that gets produced, like whether it's a table, a view, or materialized view. Storage format, for example, we may choose whether it's an iceberg or a parquet, as well as partition and clustering scheme. The attributes that don't impact data are the ownership information, model column definitions, SQL comments, as well as code formatting. Those things don't have any impact whatsoever on the output of the model. Now I can take these values on the left-hand side, hash them, and call the resulting value a data hash. I can do the same to the right-hand side group and call it metadata hash. Now, if I put these two values together, I get what I call model fingerprint, which basically a unique identifier of a model version. So we just versioned our model. What can we do next? So we can take the original model definition with all its attributes, queries, etc., together with its fingerprint, which is a unique identifier of specific model version, put them together and call this model snapshot. Now, this has nothing to do with DBT snapshot. It's a completely separate concept. We can then take this model snapshot and store it in some state, record it for prosperity. So now we have a historical record of all the changes we've made. Snapshots, though, have a series of properties which are very important. Property number one, it's a model frozen in time. That means that every time you change a model, a new snapshot gets created. Furthermore, snapshots are uniquely identified by the model fingerprint. This means that no two snapshots can exist with the same fingerprint. They are self-contained, meaning that when we package the model definition into a snapshot, we also include all the relevant dependencies, like, for example, macros, so that we can completely recreate the model behavior at a certain point in time. Finally, snapshots are immutable. Once created, they can change later in time. Okay, so we just versioned the model definition. We figured that part out. But how do those definitions, how do those versions map to objects, like various tables and views in your data warehouse or data lakehouse? Well, as it turns out, the mapping is actually very straightforward. So every time you change your model, a new snapshot gets created, and a separate table or like data object gets assigned to it in the data warehouse. So imagine we were to change model A, for example. Well, we will create a new snapshot, and we will get a new table for it. Let's recap. Model fingerprint uniquely identifies a specific model version. Model definitions like queries, its attributes, and alongside all its dependencies are packaged into self-contained snapshots. Each snapshot gets its own table or a view or any other kind of data object in the data warehouse or data lakehouse. All right, we kind of figured the versioning part out, right? But how do we access various snapshot tables? How do we know which one to access to begin with at any given point in time? Well, this is where visual data environments come in. So we are going to split the data warehouse layout into two layers, virtual layer and physical layer. So please note that no such layers actually exist anywhere. This is just a mental construct we use to help us reason about the various data objects that we're going to introduce here. Now we already know what to put into the physical layer. This is the snapshot tables that we just talked about, the versioned one. What about the virtual layer? Well, the virtual layer is just a set of views with well-defined names which point to the snapshot tables using a simple select star from expression. So the downstream consumers, instead of accessing the snapshot tables directly, they access model data through those views. Now we can congratulate ourselves because we just invented pointers. But why? Why do we need this kind of interaction? Well, let's group these views that we just created, put them into an imaginary box, and call it production environment. Now, if we were to make some changes, we will need development environment, right? So let's go ahead and create more views, put them in a different box, and call it development environment. Now, notice how the views in the development environment point at exactly the same snapshot tables with actual data as the production environment views do. So we effectively created a complete clone of production without a single computation other than some metadata operation required to create views. All right, so we created the environment, but now we need to make a change. So let's imagine we change model A. Well, a new snapshot gets created, and a new table gets created for it as well in the physical layer. Next, we're going to update the view in the development environment to point at this new table. Note, however, that production environment remained completely unchanged. Those views still point at the old tables. So this is how we can ensure isolation. Only development environment is impacted in this case. Please also note that the model B hasn't changed. So no new snapshots have been created for it. So the data for that model is shared and reused across both environments. That also means we can use the same data for downstream dependencies. All right, we're done iterating with model A. On model A, we are ready to deploy the change back to production. Well, you might be expecting that, but what we're going to do, we're going to simply update the view in the production environment to point at the new snapshot table. So note that all the necessary computation, all the necessary backfilling could have happened before we did that. We could have run everything while iterating in development, and then the only step that needs to be taken here is actually changing the view. So the deployment to production can happen almost instantaneously. or the time it takes to update that view. Yeah, so I'm already picking up some skeptical looks in the audience. You're probably thinking, Iaroslav, creating new tables from scratch is nice and all, right? But what if? What if the table is too large and costly to rebuild? What if the model logic is not idempotent, meaning running the same query multiple times yields different results? What if the historical data is not available upstream, meaning there is nothing to rebuild from? These are all very legit concerns. Sadly, however, you're out of luck. Follow me for more advice on how to build data pipelines at scale. No, I'm just kidding. I'm just kidding. So we can address this with a concept called forward-only change. So what does it mean? So let's revisit our development use case. But this time, and by the way, it's called forward-only because the changes are applied going forward as opposed to retroactively. So instead of creating a new table from scratch, we can determine which table is currently promoted in production and make a shallow clone of it, or also known as zero-copy clone, depending on the engine. So now we get a complete preview of the change in the development without impacting production, but also without backfilling the whole data from scratch. Well, now when we go to prod, instead of updating the view, we actually apply the changes, the necessary changes, directly to the same snapshot table that we used before in production. So we will update the schema accordingly and continue writing into this table, preserving this way the historical context. This is the forward part of the forward-only change. Now the trade-off, of course, is that rolling back a change is no longer as straightforward. You potentially need to explicitly run a data restatement process, which entails additional computation. Now, if we make additional changes to the model A, it's just like a rinse and repeat. We clone, and then we evolve that same table all over again. Let's recap. So data warehouse gets split up into two layers, a physical layer and virtual layer. The physical layer is where versioned model tables reside. This is where actual data is stored. The virtual layer is a set of views that point at the set of views with well-defined names that point at various snapshot tables. Environments are just collections of views. Using them and creating them is very fast and cheap, and they are always populated with up-to-date representative data. Now for the next pillar, the automatic data contracts, rely on the concept of semantic understanding. But what does it mean? What is semantic understanding? Well, let's revisit a query from the first slides. We can parse this query into a tree-like structure that we call abstract syntax tree, or AST for short. So you can see that this tree-like structure directly represents the query that we wrote. Now, using this representation of a query, we can do various things. We can figure out the upstream dependencies. We can determine the column level lineage and many other cool things. And one such cool thing I'm about to show you. Let's imagine we change the query. We add a new projection to it, projection D in this case, right? So now our tree goes from looking like this to looking like this. We can clearly see that a leaf node, a new leaf node, have been added under the select node. What does it mean? Well, it means that unless downstream models use select star query, which we shouldn't do, we know that that no downstream dependencies are impacted by the change, that the change is non-breaking. We haven't changed the cardinality of the output or number of rows. We haven't changed the logic. We just added a new column. So we can only backfill the model that we just changed in order to accurately preview the change and in order to reflect it in production. Also note that we don't need to evaluate upstream either. Since those models haven't changed, we can just reuse the data that is already there, those snapshot tables that are already there, in order to feed the data into the impacted model. What about a break-in change? Let's say instead of adding a new projection, we adjusted a threshold for C and changed it from 0 to 100. Well, now our tree looks like this. So instead of adding a new leaf node, we actually changed the existing one. What it means is that it has direct impact on downstream models and consumers because we changed the number of rows that will be in the output. So we do need to backfill the downstream models in order to correctly preview and reflect the change in production. Note, however, that we still don't need to do this for upstream dependencies because nothing has changed there. Let's recap. So the semantic understanding leads to our ability to categorize changes into breaking and non-breaking. This, in turn, allows us to preview or assess the impact of our changes before a single execution takes place. Furthermore, this allows us to drastically reduce the amount of necessary computation for non-breaking changes, which also naturally encourage users to make fewer breaking changes. So now we are ready to finish the construction of this little Parthenon. Data versioning ensures that we can easily go back and forth between the changes we made. It unlocks paths to virtual data environments, which are further enhanced by automatic data contracts. Virtual data environments provides a cost-efficient way for users to get a complete and accurate preview of their changes using representative data, while also ensuring safe deployments to production. Finally, automatic data contracts ensures fast feedback loop by assessing the impact of a change long before anything actually runs. Additionally, it reduces the necessary computation drastically for non-breaking changes. Put this together, and you get fast, safe, and cost-effective development process. So we are done with the theoretical part of the talk, and about to transition into a practical one. So if you thought that these ideas were too abstract, I'm about to show you how this works in practice. So I'm going to show these ideas on SQLMesh. And everything I'm about to show you is completely free and open source, including the UI, by the way. A few words about SQLMesh. That's an open source data transformation and modeling tool, as I mentioned earlier. It uses only SQL for its definition. You never have to write a single line of Jinja in your code. It comes with batteries included. Things like data interval tracking, a la Airflow, unit testing, CI/CD integration, Airflow integration, etc. All is there. It's backward compatible with dbt, which means that you can use it as a drop-in replacement for dbt core on your existing project. Finally, and most importantly, it brings the 3 pillars of data productivity to life. So everything I talked about so far are essentially the core fundamental concepts of SQLMesh. So initially, I was going to show you a video, but there were some technical difficulties with that. So I have to fall back to my backup, and unfortunately, my backup is a screenshot of the video, which is very meta. Don't ask me why. I think I was just too lazy to replicate the demo all over again. So I'm going to show you some screenshots, and hopefully you can enrich them with your imagination. So this is a SQLMesh UI, and you can see that at the bottom there is some lineage displayed, including the column level lineage. At the top, you can see an editing screen, and this is what the typical model definition looks like in SQLMesh. As I promised, no Jinja, pure SQL. And this definition is exactly the query that I showed you earlier. Now we're going to make some changes to this in order to show off what can be done, what kind of capabilities are there. So we're going to first create a development environment. So we're going to click that environment name drop-down and create a new environment. It's not like you will have to trust me that it's an instantaneous process. Then we're going to go ahead and add a projection to the query. Now SQLMesh immediately picked up that there is one directly modified model. A model is named target. It also immediately determined that there is one indirectly modified model called downstream. Now, in order to apply changes, all changes in SQLMesh are applied through a single command. It's called plan. How many people here are familiar with Terraform? Oh, a lot more than SQLMesh. Well, we got to correct that. Basically, SQLMesh was heavily inspired by Terraform. And a lot of the concepts we basically tried to mix, like we are big fans of Terraform, and we really tried to bring these concepts of deployments to data. So SQLMesh also has a plan command. And you see like that green button over there. This is how you apply changes. So you click plan, and the plan is a way to preview your changes before actually applying them. And you can see that SQLMesh automatically categorized my change as non-breaking. Now I can, of course, disagree with SQLMesh. And I can reassign a change category and say, well, no, you were wrong, it's actually breaking. But another thing to pay attention is, when it comes to backfills, basically what will be evaluated, we can see that only target model needs to be evaluated because the change is non-breaking. And the source, which is also a model in this project, it hasn't changed, so we can just reuse the data from it. We will go ahead and apply the plan, and we see that it got evaluated successfully. And now we will try and connect what we just saw with what we learned earlier. So we have two environments, production and development, and you see the views in those environments have well-defined names, as I mentioned previously. So the production views, they have names that match the model names. So dc.target, dc.downstream. How about the development environment? Well, in case of the development environment, we added a special suffix with an environment name to the schema portion of the model name. This is how you can differentiate and switch between environments and still get access to the data there. So if I were to check out my changes, I would query dc__dev.target instead of dc.target. Also notice that the view in the development environment points to a new version of the snapshot table, while the downstream remained unchanged. Oh, in case if it wasn't clear, the new projection D is actually in this new snapshot table. Now, how about the breaking change? Same thing. So we're gonna modify the query, change the threshold. SQLMesh picked up one directly modified model. We run plan, boom. SQLMesh says, no, it's actually breaking. It's breaking. How about the backfills? Well, this time, we need to backfill both the target model and the downstream one in order to test the changes accurately. I'm going to go ahead, apply the plan. Now, the last thing I wanted to show you, deploy into production. So we just introduced these breaking changes. We already evaluated it in development. Now we are ready to deploy this to production. So we're going to select a prod environment in a drop-down, and we're going to run plan again, because all changes are applied through the same command. So SQLMesh again picked up that the change is breaking. However, there is one crucial difference. There are no backfills. We don't need to evaluate anything. We already did that while iterated in the development environment. And since nothing has changed since the last change we made, we can safely reuse the data when going to production. And you see, SQLMesh even helpfully suggests that what we are about to apply is virtual update, which means we only make update to virtual layer of our virtual data environments, and we don't actually materialize any data. There is also a helpful prompt to make sure that I know what I'm doing when I'm deploying to production. And we are done. That's pretty much all I have. Thank you all for coming. Join our Slack community. This is a QR code for our Slack community to talk about SQLMesh, to talk about SQL Guard, and other exciting things that we at Tobiko are working on. Thank you all.